On-off controllers are simple, yet they are important devices. They help control things like temperature, pressure, or even light. Many machines and appliances use them. They are used to keep things at just the right level. You can find on-off controllers in homes, factories, and even in cars. These controllers make choices that are very easy to understand. They can only do two things: turn something on or turn it off. There is absolutely no in-between. This makes them simple to use and also easy to understand. But simple does not mean that they are unimportant. In fact, on-off controllers are commonly found in many places. They are the brains behind the devices that keep us comfortable, and more importantly, safe. As we go through this essay, you'll see exactly how these controllers work, and also the problems that they can have. We will also explore how something called a neutral zone makes them even better. An on-off controller is like a basic switch, but with a smart brain. It measures something like temperature or pressure. Then it compares this measured value to a set point, which is the level you actually want. If the measured value drops below the set point, the controller turns on. If the value goes above the set point, it turns off. It is always checking, always ready to switch. Think of it as having only two possible choices. There is absolutely no halfway. It is either fully on or fully off. This makes the controller easy to understand and easy to build. This simple switching behavior is very effective for many jobs. However, as we will see, this basic approach has some drawbacks that need fixing. Let's take a closer look at a typical home heater. We'll explore its basic operation and how it maintains a comfortable temperature in your living space. We're going to focus on how the on-off control works, which is the most fundamental aspect of its operation. Imagine a cold room, perhaps on a chilly winter evening. The furniture is shivering and the air is crisp. You set the heater using its thermostat to keep the room at a cozy 70 degrees Fahrenheit. This is your desired temperature. That's equivalent to 21 degrees Celsius for those who prefer that scale. The heater is equipped with a sensor, a crucial component for maintaining the set temperature. This sensor constantly checks the room's temperature, acting as the eyes and ears of the heating system. When the temperature drops below 70 degrees, indicating that the room is getting colder than desired, the on-off controller springs into action, turning the heater on to generate warmth. The room gradually warms up, chasing away the chill. When the temperature rises and goes up to 70 degrees, reaching the desired level or even a little higher, exceeding the set point, the controller responds by turning the heater off, preventing it from overheating the room. Now the room begins to cool down again as the heater is no longer generating heat. This cycle of heating and cooling repeats again and again, maintaining a relatively stable temperature. The heater keeps turning on, providing warmth when needed, and off, conserving energy when the desired temperature is reached. This ensures the room stays close to the set point, providing a comfortable environment. The controller operates in a binary fashion, never doing anything halfway or partially. It is always either heating at full capacity or not heating at all, with no intermediate states. This simple on-off system works well enough for many applications, providing basic temperature control. But sometimes, this basic control method can have problems and limitations. This is especially true if the temperature changes quickly or if a more precise temperature is needed. Section 4. The problem of rapid switching. It's a common issue with simple control systems, and understanding it is key to building more robust and reliable automation. Basic on-off controllers can, switch on and off too often. This rapid cycling can lead to a host of undesirable consequences. This usually happens when the measured value hovers right around the set point. The controller is constantly trying to correct minor deviations. For instance, if the room stays close to 70 degrees Fahrenheit, the heater could keep switching quickly. It's a constant battle to maintain that precise temperature. This fast switching is called chattering or rapid cycling. It's a telltale sign that your on-off controller is struggling. It's really not good for the equipment. The constant stress takes its toll. Turning on and off again and again can actually wear out switches and parts. The mechanical components simply aren't designed for that level of activity. Plus, it uses more energy and can shorten the life of the appliance. The frequent power surges and thermal stress accelerate wear and tear. Rapid switching can also be, well, pretty annoying. You might hear clicks or see lights flicker as things turn on and off too quickly. It's a constant reminder that something isn't quite right. In some cases, it can even damage the whole system. The cumulative effect of rapid switching can be devastating. So, while on-off control is simple, it can cause problems when the process variable stays near the set point. It's a limitation that needs to be addressed. That's where the neutral zone comes in. It offers a solution to this persistent problem. Section 5. Let's delve into why neutral zones matter so much in control systems. Understanding their significance can greatly improve the efficiency and longevity of various processes. A neutral zone, also called a hysteresis zone, is a range of values where no action is taken by the controller. It's a clever solution to prevent rapid and often unnecessary switching. It adds a small buffer around the set point, creating a zone of inaction. The controller doesn't switch on or off, remaining in its current state, unless the value goes outside this buffer, exceeding the defined limits of the neutral zone. For example, if you set the heater's neutral zone to 2 degrees Fahrenheit, meaning 1 degree above and 1 degree below the set point, it will turn on at 69 degrees, the lower boundary of the zone, and stay on until the room reaches 71 degrees, the upper boundary. Only then will it turn off, preventing it from short cycling. This stops the controller from switching too often near the set point, reducing wear on the components. The neutral zone makes on-off control much smoother, leading to more consistent performance. It helps protect equipment, extending its operational life. By reducing wear and tear caused by frequent switching, it also saves energy, minimizing unnecessary operation, and makes the process more stable, ensuring consistent output. In short, the neutral zone makes simple on-off controllers, which are often the most cost-effective, smarter and safer, enhancing their overall performance and reliability. It's a small change that makes a big difference in everyday life, improving efficiency and reducing maintenance.